Welcome to the problem-solving set on linkage and mapping review. Question 1. A pure breeding strain of few flower milkweed, Asclepias lanceolata, is homozygous dominant for the genes determining leaf size, S, stem height, H, and flower color, C. The white stem milkweed, Asclepias albicans, is homozygous recessive for these three traits. All three genes are linked on the same chromosome as shown in the following diagram, where H and C are 10 map units apart, and C and S are 16 map units apart. A hybrid offspring between these two milkweeds is crossed back to a white stem plant. Answer the following questions assuming no interference. So let's first diagram this cross. You have the hybrid between a few flower milkweed and a white stem milkweed. And this hybrid would be big H, big C, big S on one of its chromosomes, and little h, little c, little s on its other chromosome. And they're saying it's crossed back to a white stem milkweed, which is little h, little c, little s, little h, little c, little s. So the first question is asking what percentage of these offspring will resemble either the few flower milkweed or white stem milkweed for all traits. Well, how do you resemble these milkweeds? Few flower is phenotypically big H, big C, big S, whereas white stem is phenotypically little h, little c, little s. Now, because we're test crossing with a white stem flower, that means that the only gamete they can get from this individual is little h, little c, little s, which means that the gamete they get from this individual will be what determines phenotype. Now, the only way to have a parental phenotype or parental gamete is to not have a recombinant gamete. So why don't we look at all the ways you could be recombinant and then do 1 minus all of those ways, which would equal the amount of parental. So how can you be recombinant here? You could have a single crossover event between H and C. You could have a single crossover event between C and S. Or you could have a double crossover event, where the middle gene flips. So let's look at the double crossover event first and find its percentage. So the percent of double crossovers, again we're going to use the probability product rule to find this percentage. And we're assuming no interference, so it's not going to be any different than what we predict. So you would use 0.1, which is the percent recombination between H and C, and 0.16, which is the percent recombination between C and S. If you multiply these together, you get 0.1 times 0.16, and that equals 0.016. Now let's look at the percent single crossover between H and C. So percent single crossover between H and C. Now, because H and C are 10 map units apart, you would think that the percent recombination would be 10%. However, sometimes when there's a crossover between H and C, it's part of the double crossover event. So what we're going to do is do 0.1, which is the total percent, minus the 0.0116, which is the percent from double crossover. So when you do this, you get 0.084. Now let's look at the percent single crossover between C and S. Again, you would think it's 0.16, but you have to account for the percent of double crossovers. So it's 0.16 minus 0.016, which is 0.144. So these are all the ways to get a recombinant gamete, which would give you a recombinant phenotype, and that's not what we're looking for here. We're looking for the parental phenotype. So if you add all these together, you get 0.016 plus 0.084 plus 0.144, and that equals 0.244. And remember, this is total recombinance. So to find parental, all you have to do is 1 minus 0.244, which equals 0.756. And in a percentage form, you just times that by 100%, and you get 75.6%. And that is the percentage of the offspring that will resemble either the few flower milkweed or the white stem milkweed. So 75.6%. Okay. For part B, it's asking 1% of the backcross offspring will have stem height and leaf size resembling the few flower, but flower color of the white stem. So remember that flower color is designated as gene C. So it's asking which will resemble height and leaf size of the few flower, which is dominant. So they want big H and big S, but have the color of the white stem, which is little c. Again, this is the parental individual that can give you recombinant phenotypes because they're the only ones that can give you recombinant gametes. So let's rewrite them and see how we would get a big H, little c, big S. So this individual is big H, big C, big S, little h, little c, little s. And the gamete that they want is big H, little c, big S. And remember, that's because they're crossing with little h, little c, little s. So phenotype, this would be big H, little c, big S. So how would you get that gamete? Well, you would have to do double crossover. If you follow it, big H, follow it down, little c, follow it back up is big S. Now remember, double crossover is what we found above to be 0.016. However, we're only interested in one of the double crossovers. Remember that there's another way to follow this, little h, big C, little s. And we're only interested in this double crossover. So we're going to divide that by 2. Get 0.008, and as a percentage, we're going to times by 100 and get 0.8%. So that is the percentage of the offspring that will have that phenotype, so 0.8%. Finally, for part C, it asks what percent of the backcross offspring will have stem height and flower color of the white stem, but leaf size of the few flower. Remember that leaf size is gene S, so it's asking for height and flower color of the white stem, which remember is recessive, so little h, little c, but have leaf size of the few flower, which would be dominant, big S. So how would you get that phenotype? Again, it's the same parent that can make recombinant gametes. And this time, you want little h, little c, big S. And how would you get that? Well, you would just need a single crossover here between gene C and gene S. So you would have little h, little c, big S. Now remember, this is only one out of the 2 recombinant gametes that come from this crossover, because the other one is big H, big C, little s. So first, let's look, what did we find was the percent single crossover between C and S? We found it to be 0.144. And because we're only interested in one out of the 2 recombinant gametes that come from this, we're going to divide that by 2. And times by 100 to get percentage, and we get 7.2%. So that is the answer for part C. Genes AB and PC are 8.2 centimorgans apart, and genes PC and RO are 34 centimorgans apart, with PC located in the middle. What percentage of offspring would be double crossover recombinants, assuming no interference? So genes AB and PC are 8.2 centimorgans apart, and genes PC and RO are 34 centimorgans apart. And they're asking for percent offspring that exhibit the double crossover phenotype. So how do you find that? Now remember that every centimorgan means 1% recombination. So the percentage of recombination between AB and PC would be 0.082, and the percentage recombination between PC and RO would be 0.34. And we're going to use the probability product rule because to get a double crossover, you would need a double crossover between each region. So if you multiply these together, you get 0.082 times 0.34, and that times 100 to get percentage equals 2.788%. So you times by 100%, and you get 2.788%. And that is the percentage of the offspring that will be double crossover recombinants. Problem 3. 3 genes are present on a chromosome as shown below, with A and B 20 centimorgans apart and B and C 10 centimorgans apart. A completely heterozygous male is test-crossed to a female homozygous recessive for the 3 genes. Out of the 1,000 offspring produced, 8 were double crossover recombinants. What was the frequency of interference? So let's remember some formulas. Remember that interference, which is the phenomenon where double crossovers actually occur less than what you would predict. Interference equals 1 minus the coefficient of coincidence. And the coefficient of coincidence is equal to the number of observed divided by the number of expected or predicted. Okay, so let's find the number of expected, because we know that the number of double crossovers observed is 8. So now let's find expected. For expected number of double crossovers, first you need to find the percent frequency for double crossovers, and you do that by using the probability product rule, where the probability of a crossover happening between A and B is 0.2, and then a probability of having a crossover happen between B and C is 0.1. And to get the expected number, you would times that by 1,000 offspring. When you do that, you find that the expected number is 20. So now we know expected is 20. So what is the coefficient of coincidence? CC is equal to 8 over 20, which is 0.4. However, they're asking for the frequency of interference. So for interference, we have to find 1 minus 0.4. So our answer is 0.6. Problem 4. A nematogeneticist determined that 4 genes, short length, gene L, cream-bodied, gene C, segmented, gene S, and black eyes, gene B, are all located on the same chromosome. She does a series of test crosses to obtain the following map distances. What is the order of genes on this chromosome? So these are a lot of map distances and it may seem overwhelming, but there's a simple approach to it. So first you want to look at, out of the 4 genes, which 2 are on the end, or in other words, which 2 are most far apart. So if you scan through, you can see that C and S are 49 centimorgans apart, and that's the largest map distance that she found. So we're going to put C on one end and S on the other, and say that total, that is 49 centimorgans. So basically the line that we drew here is 49 centimorgans long. Now, let's work from one side on. So first, let's look at CB and CL. From these map distances, you can see that C is closer to L than B. So for B, if C to S is 49 centimorgans, C to B is 42, so B is relatively close to S. By the same token, C and L are 36 centimorgans away, so L is a little closer, but not that much. Now we can look at the other distances to double check. If you look at S to B, that's 13 centimorgans. So we'll say this is 13. S to L is 19 centimorgans. So here is 19. And L to B is 6. And if you add 6 and 13, you get the 19 centimorgans. And then total here, which was the first thing we did, C to S is a total of 49 centimorgans. C to L was 36. And C to B is 42. So the order of genes on this chromosome is C, L, B, S. That's of course looking if C is on the left side. It can also be looked at from S on the left side, which would be S, B, L, C. So either way, these are the order of genes on this chromosome. Problem 5. Jen, the geneticist, wants to know if two dogs' genes, ear length L and spots S, are linked. She mates a pure breeding spotted dog with long ears to a pure breeding solid colored dog with short ears. The offspring were spotted with long ears. When two of these heterozygous dogs were mated, the offspring included 5 long-eared spotted puppies, 4 short-eared spotted puppies, 3 long-eared solid-colored puppies, and 4 short-eared solid-colored puppies. For A, what are the expected number of offspring for each phenotype if the genes for ear length and spots are unlinked? So let's define our alleles first. So there's ear length, which is gene L, and there's spots, which is gene S. Now, which one is dominant? When you look at two pure breeding homozygous individuals crossed with each other, the heterozygotes, or offspring, were spotted with long ears, which is what I highlighted. That means that spotted is dominant over not spotted, and long ears is dominant over short ears. So let's define spotted as big S and little s will be solid color, no spots. Long ears will be big L and little l will be short ears. So for A, what are the expected number of offspring for each phenotype if the genes for ear length and spots are not linked? So they're talking about two F1 individuals crossed. And remember that those F1 individuals are heterozygous. So let's write down their genotypes first of all. The parental generation were pure breeding spotted dog with long ears, so big S, big S, big L, times a pure breeding solid color dog with short ears, so little s, little s, little l, little l. So all the F1 offspring were big S, big L, little l, which is a dihybrid individual. Okay. Part A is asking if these genes are unlinked, what is the expected number of offspring of each phenotype? So if you cross two doubly heterozygous individuals and they're unlinked, you would get a 9 to 3 to 3 to 1 ratio because that's just a dihybrid cross. Now that corresponds to big S, big L, which would be spotted with long ears, three would be big S, little l, spotted with short ears. Little s, big L, solid colored with long ears. And finally, little s, little l, which would be solid color with short ears. Okay, so this is what we would expect. Now, how many total offspring did they have? It was 5 plus 4 plus 3 plus 4, which is 16. So offspring total is 16. Which means that we don't have to multiply here because this total is 16. So these are good for our expected chi-square numbers. Okay. Now it asks, what is the calculated chi-square value? Again, chi-square is the summation of observed minus expected squared over expected. So for the first class, spotted and long-eared, we expected 9, and we observed, let's see, spotted with long ears, we observed 5. So it's 5 minus 9 squared over 9. For spotted with short ears, we expected 3, and short-eared spotted puppies we had 4. So we observed 4, expected 3. For a solid color dog with long ears, we expected 3, and we saw 3. Again, we know this term is going to turn into 0 because 3 minus 3 is 0. And for the last, solid color with short-eared, we expected 1, and we saw 4. So 4 minus 1 squared over 1. So let's do these calculations. We have 5 minus 9 is negative 4. We square that would be positive 16. So 16 over 9 would be 1.7 repeating. So 1.777. Okay. Then 4 minus 3 would be 1. Squared would be 1 over 3 is 0.333 repeating. The third term is 0. And 4 minus 1 is 3. Squared is 9. Divided by 1 is 9. So let's add those up. We have 1.77 repeating plus 0.333 repeating plus 9. So total we would have 11.11 if we round it off. And that is our chi-square value. Now what are our degrees of freedom? Remember, we have chi-square 11.11. And degrees of freedom, there are 4 different phenotypic classes, which means that we would have a 3 degrees of freedom. Okay? It says, based on your calculations, are the genes linked or unlinked? If concluded that they're linked, determine relevant map distances. So first we have to look at a chi-square table, looking at the degrees of freedom of 3, and see where 11.11 falls. So we have 3 degrees of freedom, and where would 11.11 fall? It would fall somewhere in here, which means that we would reject our null hypothesis. Now remember, our null hypothesis is always that genes are unlinked. And that's how we determine the expected values. So if we're rejecting the null hypothesis, that means that these genes in fact are linked. And now we have to determine relevant map distances. So again, let's do the parental cross, but this time we're going to draw it as if they're linked. So for the parents, they were both pure breeding, right? So this first parent would be big S for spotted, big L for long on both chromosomes. And the second parent would be little s for solid color and little l for short on both chromosomes. Which means that all F1 individuals were big S, big L on one chromosome, little s, little l on the other. Now what genotypes can these F1 individuals make? They can make parental gametes, which would be big S, big L, little s, little l, or they can make recombinant gametes, which would be, if a crossover happened here, big S, little l, and little s, big L. Okay. So now they're asking, we need to calculate relevant map distances. So to do that, map distances, again, remember, is percent recombinance in just a different unit. And that equals the number of recombinant offspring over the total number of offspring. Now remember, we said the total number of offspring were 16 puppies. But which one would be recombinant? Recombinant phenotypes would be having spots with short ears, because that was not a parental, and having a solid color body with long ears. So let's see. Okay, so we have spotted with short ears, 4 short-eared spotted puppies, and solid with long ears, so 3. So we have 4 plus 3 is 7. 7 out of 16. And then you would times it by 100 to get the percentage. So you get 43.75% recombination. And remember that for every 1% of recombination, that equals to 1 map unit or centimorgan. So the map distance between these two genes is 43.75 centimorgans. Question 6. The met and lyse genes of yeast are auxotrophic for methionine and lysine respectively. The offspring of the cross between a dominant met recessive lyse haploid yeast strain and a recessive met dominant lyse strain underwent meiosis to yield the following tetrad types. So let's first label what these tetrad types are. Remember that what we're going to call as parental gametes will be dominant for one of the genes and recessive for the other. And what we're going to recall as recombinant gametes are going to be either dominant for both or recessive for both. And that's because neither of those represent the parents, as we would call them. So let's go through and label the parental and recombinants. So the first one, you have dominant met recessive lyse, that's parental. Recessive for both is recombinant. Dominant for both is recombinant. And recessive met dominant lyse is parental. For the next tetrad type, all of them are either dominant for one and recessive for the other, and they just flip, so they're all parental. And finally, the last ascus is dominant for both, which are both recombinant, or recessive for both, which is also recombinant. So let's look again at the first one. If there's 2 parental and 2 recombinant, that means that this is a tetratype. And remember that those come about from a single crossover event during meiosis. The second one is all parental, which means it's a parental ditype. Remember, ditype means that there's 2 different kinds of gametes in this ascus, and they both resemble what we would call parental. And these occur from no crossing over. The last one has all recombinant gametes. Now this is non-parental ditype, and again there's 2 different kinds of gametes, either they're both dominant or they're both recessive, and neither represent what we would call the parental, so they're non-parental. And this occurs from a double crossover event, which happens between all 4 chromatids. So for A, what are the observed number of parental ditype and non-parental ditype tetrad types? So we saw above there are 20 parental ditypes and 2 non-parental ditypes. Part B. What are the expected values for parental ditypes and non-parental ditypes based on the hypothesis that the methionine and lysine genes are on different chromosomes? So remember from the theory video that Professor Schmidt recorded, the first rule of what you would look for if the genes are linked or not linked. If genes are linked, you would expect to see many, many more parental ditypes than non-parental ditypes. However, if they're unlinked, you would expect to see about the same amount of parental ditypes as non-parental ditypes, and you wouldn't expect to see any tetrad types. So the hypothesis here is asking if they're unlinked, what numbers do we expect? Well, we're not looking at tetratypes now, so for total we have 22 total parental ditypes and non-parental ditypes. And if they're unlinked, we would expect to have an equal number of both, which means we're expecting 11 of each. You just divide that by 2. 22 divided by 2 is 11. So this is our hypothesis, and if we're going to use the chi-square value to determine if our hypothesis is correct or incorrect, these are going to be our expected numbers. Okay? So part C, what is the calculated chi-square value? Remember that chi-square is the summation of observed minus expected squared over expected. So for the first class, parental die typed, we observed 20 and we expected 11. For the second class, we observed 2 and expected 11. So let's do these calculations. We have 20 minus 11 is 9. 9 squared is 81. Divided by 11 equals 7.36 repeating. The second one, 2 minus 11 is negative 9, squared is positive 81, and again over 11 is 7.36 repeating. And when you do the summation, you have 7.36 repeating, just multiply that by 2, and you get 14.727, which we can round up to 14.73. So this is our chi-square value. For D, it says, based on your calculations, would you reject or accept the hypothesis that these genes are on different chromosomes? So what is our degree of freedom? Remember that we're only looking at 2 classes here. We're looking at parental die types and non-parental die types. So our degree of freedom equals the number of classes, which is 2, minus 1. So we have 1 degree of freedom. So let's look at the chi-square table and see in the 1 degree of freedom, where does 14.73 lie? So we're in degree of freedom 1, and where is 14.73? It would be way down here, right? Which means that there's a less than 0.1% chance that these deviations from expected values are from random chance, and therefore we reject the null hypothesis. So we're going to reject the null, and remember our null hypothesis is always that genes are unlinked. So we're going to say that in fact genes are linked. Okay. Now this is the end of the written problem, but now that we found out that these genes are linked, why don't we find out map distance? Now remember, the general formula for map distance is always going to be the number of recombinants over the total number times 100. Now in fungi, when you have these tetrads, there's a little bit different way to do it. You do the number of non-parental die types plus the number of tetratypes divided by 2 over the total asci. Now remember, we do this because all gametes in the non-parental die type asci are recombinant, but only half the gametes in the tetratypes are recombinant, which is why we divide by 2 here. So let's do these numbers. We have 2 non-parental die types and 78 tetratypes. So we have 2 plus 78 divided by 2. And if you look, the total number of asci we have was 100. And remember that this is actually multiplied by 100 as well. So we can cross out these and just do 2 plus 78 divided by 2. So 78 divided by 2 is 39, plus 2 equals 41. So that means there are 41 map units between the methionine gene and the lysine gene.
Let's look at the true-false problems for this section. All of these problems are likely to be about linkage or something related to it, so let's check it out. Number 1, genes on the same chromosome are said to be linked. Well, the answer to this is true, but just be a little bit careful, because by definition, that's what linkage is, genes on the same chromosome. A chromosome is a linkage group. Just remember that if genes happen to be far apart on the same chromosome, they may appear unlinked. That is, they will act similarly to genes that are in fact on different chromosomes, but definitely true. Number 2, Drosophila have 6 chromosomes. Well, I'm not sure you'd really have to memorize this, but it can't hurt, I suppose. This is just the way it is. In Drosophila, n equals 4 and 2n equals 8, so this is false. Crossing over occurs during anaphase of meiosis 1 in number 3. Well, that's definitely false, because when does crossing over occur? It is in meiosis 1, but it's during prophase of meiosis 1, right? When the homologous pairs intermingle very intimately. True, false, and false. Number 4. The maximum recombination frequency between 2 genes is 50%. That's true, and I don't think this is the time to go into a massive explanation about why that is. If you've watched the theory videos, we spent some amount of time explaining why it is. But the quick version is that independent assortment gives you 50% recombinance. So crossing over can never exceed that. 50% is the max, so that is true. The probability of interference is equal to 1 minus the coefficient of coincidence. Well, yes, interference and coincidence, so they're basically the opposite of each other. Coincidence refers to the number of crossovers you expect to see. Interference refers to the ones that you expect to see that don't in fact occur. So if you take 1 minus the ones that you do see, I'm writing it over again, I guess. 1 minus coincidence. Because the point is, 100% would be, again, this is something, if we go into all the math, it would take a lot of time. The coefficient of coincidence refers to those that you predict to see that you actually do see. So 1 minus that would equal the interference. If you need more information about that, you can refer to one of the theory videos. So that is true. 6 is talking about the chi-square formula. Is it sigma observed minus expected squared over O? No, because that's right except for one thing. It's not comparing the observed minus the expected to the observed. It's comparing them to the expected. So that is false. 7. The main point of the zygote in a fungi life cycle, maybe fungal it should have said, is to have a diploid cell to undergo meiosis. And that's exactly true. So that is, that is true. Fungi are haploid dominant organisms, unlike us, who are diploid dominant. So in a fungus, the only diploid stage is the zygote. It exists briefly, meiosis happens, and you get haploid spores. And last, tetratypes are due to crossovers between either gene and its centromere when genes are on separate chromosomes. If you've been going along, you've seen a lot of problems that talk about this, or at least some. But the point is that normally when genes are on separate chromosomes in fungi, you wouldn't expect to get any tetratypes. You'd expect to get PDs and NPDs, and that's it. The only way to get a tetratype in that situation is exactly due to what it says here, is a crossover between one of the genes and its respective centromere. So that's true.